So then I'll move on to other cases, and I'll teach you how to use these formulas. So here's the first one we already covered. You can also have the Peterson Stress Concentration Handbook. For example, that book will provide formulas for various scenarios. So given the diameter of the hole, given the width of the hole, you can then come to these kind of curves, for example, and you can calculate what KT is. So in this case, say for example, that, and let me just give the scenario that we've analyzed already. Say that D over W was such that W was like infinity. It was so large. This W is infinity, basically. So that means this is near zero. And that's this point here. And you can see starts at 3, which is what we got earlier. But in real life, a lot of scenarios are not going to look like this. They're going to have a finite width, say. So in those scenarios, then the stress concentration factor is going to be somewhere along this line, right? Here, you will calculate stress concentration KT, and you will multiply that by sigma naught. Here, what you have is a plate now that's bent. So you have this plate that's been bent, and it has a hole. So how do you use this information? Well, you know the thickness of the plate, you know the width of the plate, you know the diameter of the hole. So you can come here, for example, if I know D over W, say the diameter was 0.5 inch, and say the width was 2 inch, well, that's going to give me a value of, say, 1/2 over 2, that's 0.25. So I'll go here and draw a 0.25 line here. And then I'll look at D over H. So say the thickness was a value of also 2 inch, as an example. Then I have what? I have a D of 1/2, because I said the diameter will be 1/2. And say H is also 2 inch to make it easy for me. This is 0.25. Then I'll see where it intersects here. Then that's my stress concentration. And KT then in this case becomes 2.2. And so I'll take this KT multiplied by sigma naught, the nominal stress, to get the maximum stress that could occur. And that sigma naught, they're telling you how to calculate that. They're telling you to enter into that equation the bending moment, to enter the moment of inertia, and they tell exactly how to calculate the moment of inertia. And then you enter the value of C. And obviously the highest stress occurs in the outer fibers, where C will be H/2 or minus H/2. Sinking.
Super.
So here, again, what I'll do is to look at, actually, I think in this one, again, a different problem where the load is applied far field, and you have to figure out how to use this formula. So again, very similar situation where you calculate KT. This one should be very simple to determine what sigma naught is, right? We should know what sigma naught is. Sigma naught should be very simple. Sigma naught in this case is this cross-sectional area there, the one there. I drew it slanted, but you know what I mean. So there's a far field stress, say that the far field stress was S. So S divided, let's say the load applied was P. So then S, the stress, is P divided by the cross-sectional area. In this case, is the thickness times, actually is going to be just D in this case. That's it, because they're telling you what D is. So this will be your sigma nominal, right? So this is your sigma nominal, really. So you take that stress and multiply by KT to get the maximum stress. And so in this case, they're giving you the radius, the width, and also D. And so you can, again, Say the radius was 0.5 inch. Say that D was, say, 2 inch. Then R over D in this case will be 0.2, I think it will be 0.25 again. You draw the line there. And then maybe W over D is 3, say. I don't know, I'm making it up. Say the width was 6 inch. Then W over D in this case is 3. So I drew the line, so that's where it intersects, and I go over here. And KT, just looking at it, maybe 2.1 or so. That's how you will do that. And that 2.1 gets multiplied, so sigma maximum then becomes 2.1 times the stress that goes along here. And that stress is the external load P divided by the nominal stress there, which is D times the thickness. So I think that's how you'll do that one. Let's look at this one. Another example. They tell you how to use sigma nominal in this case again. So in some cases, they tell you how to actually use it. And here they tell me what C is. So C is D over 2, and they tell you what I is. Again, very similar thing. They give you all the dimensions. In the previous example, if I use the same dimensions, 0.5 for R, 2 for D, that's going to give me 0.25 again. And then if I use the dimensions of W of 6 and D of 2 that I have here, W over D is 3, intersects over here. And so now again, the KT now is close to, and I'm actually really ballparking this, like say, 1.7 or so. I'll let you figure it out. That 1.7 gets multiplied by the sigma naught to give you the sigma max at the hole, near the hole. More examples. You have a stress concentration where maybe you have a situation where the plate drops from a larger width to a smaller width. What do you do with that? Very similar process. You continue and you have a fillet there. You don't want to have a square there because then it will be easier for things to crack there, right? So we normally put a fillet in the design process. And so this tells you how to calculate the stress right at the fillet. Again, very simple process that needs to be done. What about shafts? Because a lot of shafts that I worked on have this feature where you go from a larger diameter to smaller diameter and has a fillet with radius R. Well, it tells you what the sigma naught is. It tells you what A to use in the calculation. All you have to do is, the two diameters. Say the first diameter was 2 inch. The bigger diameter was say, I don't know. You just select the value of, say, 6 inch, right? So D over D is 0.3. 33 is off the chart. But well, actually, this is not how you use this. So that's how you do not use it that way. I apologize. Let's do it step by step. So we need to look at what the axis is asking for. It's R over D. So we have to look at that. So say the radius was 0.5 and D was, say, that diameter was about 3 inch. You will take that ratio and figure out where you are in these plots. And then you draw the line, and I'm making it up. I don't want to do all the calculations. And if you have this diameter and this diameter, you know which of these curves you can use. You have to figure out which curve. Whatever intersects, you go here, KT multiplied by sigma naught gives you the max stress. Same here. In this case, you have torsion of a shaft. So this gives you the torsional behavior due to a shaft. Here in this case, you have the torsional load applied. C is given to you. J, the polar moment of inertia, is given to you. So you can easily calculate this multiplied by KTS, which is this one, gives you the maximum stress you will have, max stress. If you had a moment that was applied to a shaft, and all this can be, like these three cases, you can actually do superposition. So you can analyze this first, add it to this one, and add it to this one. So if you have tension, torsion, and moment, just add all three cases, and you get the total stress due to those effects. You can have torsion of a shaft that has a hole through it. We call that a keyhole. And you can see what the stress concentrations are in this plot. More examples here. You have bending of a shaft that has a hole. That's how you'll do the calculation. It tells you what sigma naught is. All you have to do is figure out the dimensions are given to you in the design, and then calculate the KT. The KT gets multiplied by sigma naught to get the max stress. More examples, you have a pin loading a hole. So if you have a pin loading a hole, it tells you exactly how to do the calculations. It tells you that if there's clearance between the pin and the hole, you better increase KT by 35 to 50%. You can see the stress concentration is severely higher due to a plate loaded in a tension by a pin through a hole. Much more higher stress concentration due to that issue. That calculation was described in a paper by Hill. The paper was called Stress Concentration Factors Around a Central Circular Hole in a Plate Loaded Through a Pin in a Hole in the Journal of Applied Mechanics, Volume 7, Number 1, March 1940. So very, very old calculation, but it's used until today. Very powerful calculation. And notice how this distance matters. How far the hole is from the edge matters, right? So the further so say H was much greater than W, that's actually going to be good for you. It can be very good for you. But anyway, these are some things that to keep in mind. What if you have a stress concentration that looks like this one, for example? Again, very similar calculation for grooved round bar in tension. More cases. This is for torsion. At this point, I'm just going to show you the ones that are out there. And there's a little more complicated ones that you may find in industry. That one even requires a table now. I'll pause there for a second. But generally speaking, this is an approximation for stress concentration factor for bending of a round bar or tube over transverse round hole. Very complex calculation, but very, very similar process. More calculations. I'm pasting here things that could be useful for you in industry. In this case, you have a keyhole, and there's a lot of. I'm trying to show you that there's memorization is not worth it. What's important is to learn how to use this kind of calculations. I'm teaching you that sometimes I don't even know. What I'm trying to do for me to use them is to understand the figure first before I apply it. And the figure pretty much tells you what to do. For example, here it tells you KTA. Well, what does KTA mean? It tells you that at location A, that's what the stress concentration is. At location B, at the end of the keyway, that's what the stress concentration is. And it tells you exactly where point A and point B are in each of these diagrams. Unfortunately, some of these diagrams are not clear. And sometimes it can take you quite a bit of time to figure it out, to be able to use it successfully. But if you're not certain, maybe use a range that you think is reasonable in your design as an initial step, right? It's not kill you to use a range to if you don't have clarity in your design. More examples. That's torsion. This one was bending. You can see that there, bending. So pay attention to the figures to figure out what they're talking about. That's torsion. So yeah, you have to pay attention to all the figures as you're using them. What if you have an elliptical hole? For elliptical hole, you can use area stress function again. The formulas are actually quite complicated. And here you can see that the max stress in using curvilinear coordinate system is going to be, the max stress is going to be a formula that looks like this, where 2A is the width of the hole, and B is the thickness of the hole. You can see those diameters provided, or the dimensions provided there. And that shows you very clearly the stress concentration factor can be quite high. So say A was 2 times, say A was 2 times B, meaning that that length is twice the thickness of that hole. What you find then is that the stress concentration factor will be 1 plus 4B divided by B. And that's going to give you 5 sigma, which is quite a bit higher than if it was a circular hole. If it was a circular hole, then A equals B, and then this calculation becomes 3 times sigma, which is exactly what we got for circular hole. More example here, just showing you what the formula looks like for those cases. Pretty much this formula that I showed you here, but shown in a different way. You can also study other cases where you're looking at a square hole. So say you have a situation for the case of a thin wall pressure vessel under pressure. And you're studying this case, and beta here is a biaxial ratio. So you can see I'm applying a load in that direction and a load in this direction. In this case, for pressure vessel, where if I look at a pressure vessel, the hoop stress is going to be PR over T, while this stress here is going to be PR over 2T. We already covered that. So the ratio of those two stresses is a beta of 0.5, right? So that's 0.5, 0.5S. What this is showing you is what the stresses are SB and SA as a function of beta. And you can see for pressure vessel, SA is 2.5S and SB is 0.5S. So that stress here, SA is lower than the uniaxial loading condition. The uniaxial loading condition is 3S. And for an elliptical hole, a B over A of 2, you actually get a stress. This is if you're a circular hole. If you have an elliptical hole, you actually get a even lower stress concentration than if you had a circular hole, which explains why we use elliptical holes in an airplane. It actually is helpful in the design. Lugs can also be studied using curves like this. And then this is from the Stress Rourke's handbook. It shows you in table 17.1, chapter 17, various situations with the stress concentration factor provided for a lot of different cases. Outer corner, square, rounded to radius. It shows you the KT for various situations. You also have a very famous problem where you have a periodic number of holes next to each other. And these holes are going to be in a row, and you're applying a far field stress. And the question here is, hey, what is the stress concentration factor for those cases? Well, it's provided here in these formulas. And you can see here they're providing the formula for sigma 2 equals 0, and then this is the formula for sigma 1 equals 0. You also have a situation where you have this bracket, and that bracket has a load applied. So basically you have a bracket that has a shape and you're applying a load that way. Guess what? They also give you the KT for those cases. and the KT corresponds to the location of the stress concentration, which is near the fillet. You also have the case of multiple U notches in a member of a rectangular section. You can see there in case number 19. And you can quickly calculate what the stress concentration factor is for that case. Case 13, you have a square slot, which has a rectangular cross-section. Also, again, it provides you what that looks like. What if you have a reinforced circular hole with a plate? It also provides you what that stress concentration factor looks like. I'm not giving you all the formulas here because the stress works. So the stress works, let me type it for you so you know what the resource is. This handbook is very helpful. Has a lot of closed-form solutions that are very, very helpful in industry. More examples. This is a very good one. What if you have a square window with a radius of curvature at the corner of R? How you calculate stress concentration factor? There you go. That's how you calculate it. And C1, C2, C3, C4 are given here. And it tells you how to apply the stress concentration factor to the formula. It tells you to calculate KT and multiply by sigma 1, which is provided as a far field stress there. And then, again, at the bottom, you see another case study. Yet another case study. So again, I'm not going to cover each of these cases because in industry, you pull up the book and see which one applies to your case. The point I want to make is finite elements is one way to solve things, but it's not practical because you may have to do calculations that are quite complex when you could have just used a hand calculation that does a fairly good job. Now, if the stress field is exceeding the strength of the material or is yielding, then maybe finite elements may be a better way to go to understand what the effects are from that stress concentration on the nonlinear behavior of the material. More cases, other design plots for other cases shown here. This comes from the book from Boresi, Advanced Mechanics of Materials, figure 14.16. And it showed three cases, case 1, case 2, and case 3. In this case, in this plot, you can actually analyze any of these cases using a single plot. More cases here shown from figure 14.10. Here you can see more formulas being used. What if you have a notch or a hole within another hole, right? So not only you have the stress concentration from this hole, now you have a stress concentration from this hole. So typically the approach is to multiply each of those factors. First, you analyze this case for the small hole. Then you analyze this case with the big hole. You multiply the KT from this hole and the stress concentration factor from this hole. You multiply them together to get a total effect due to that. Very useful if you want to study pits within a notch. Here's an example. I have corrosion pits, right? So instead of modeling that with finite elements, you can approximate the shape of those pits, and then perhaps you're able to analyze this scenario. You can actually analyze that and you get a KT of 8. Point being here is that larger scale materials may have the same stress concentration. You can see there, same far field stress, same stress concentration, but here I have a higher area under higher stress. So this is more likely to fail because you're going to have defects in the material, more likely to have defects in the material that are above the strength of the material. More cases. So these are design guidelines for shaft. Bad idea. Sharp corner, go with rounded corners. Sharp corners, go with rounded corners. Sharp corner, go with rounded corners to relieve the stresses, right? You want to reduce that stress concentration. That corner, no, go with the fillet, right? Keyway on their shoulder, go with the fillet. Those are good design practices that you can follow. With that said, I want to thank you for your time.